Perfect. So we have all of our panelists. Fantastic. So the third session will focus on overcoming the barriers associated with automotive lightweighting and vehicle optimization. So very excited to have everyone here today for what we'll find an interesting discussion. I've had numerous conversations with the panelists, so I do believe there's going to be some exciting nuggets that they can provide. So without further ado, I'd like to welcome the following panelists. We have Robert Walus, Director of Manufacturing Engineering for Rivian; Jose Luis Galaviz, Chassis Technical Lead, Frame Group for Stellantis; Mario J. Felice, retired Global CAE Manager, Powertrain, MVH, Calibrations and Controls, Ford Motor Company; and Jacob Lyjak, Global Market and Technology Analysis Manager for General Motors. So I like to hand you over to Jacob, who will be moderating the session. And thank you very much, guys.
Okay, thank you, Mark. Welcome, guys. Welcome everyone back. Well, let's start. So let me just give you a brief intro. So we all know the world is changing pretty fast. Mass reduction is not a new concept. But there are all kinds of things that are changing right now, and I guess the question is kind of to both of you, to all of you guys. Maybe we can start with Mario, but how the question is how do you see the impact of lightweighting and mass reduction, impacting the changing world right now, what we're all experiencing.
Yeah,
Mario, if you could start,
sure.
And then maybe
you can hear me okay, correct? You can hear me okay? Yeah,
I can hear you fine.
Okay, so it's a very interesting question, and I like to preface it by saying that the auto industry right now is going through the most disruptive times that we've seen in recent history, confronting perhaps the largest technology transformation since its beginnings. And with that, the challenges are great. One is the electrification of powertrains, the reinvention of the battery, the use of smart adaptive technologies, the application of advanced control sensors, and finally the arrival of self-driving autonomous vehicles. And this is really to deliver some critical attributes like cleaner emissions, energy efficiency, consumption with much safer environment. And lightweighting in this plays a critical role. I think it's a critical catalyst to delivering these attributes. So the past focus, based on my experience, has been that the auto companies have taken significant weight out of the vehicle body and the frame with use of substantial usage of aluminum and composites. And now, as we work in moving the propulsion system from ICE engines, internal combustion engines, to HEVs, to battery electric vehicles, the focus has been more on lightweighting the propulsional system through more usage of aluminum, magnesium, composites, and plastics. So my thinking is mid and long term, the critical need is to develop lightweight material that is such as composites and plastic that is 100% recyclable. This is a great challenge. And then additionally, as the autonomous vehicles come aboard, we're moving from level 2 to level 5 full automation. Oh, I'm sorry. Hold on. Forgot to turn off the phone here. There's going to be a lot more needs for lightweighting. The vehicle will have significant feature content in the vehicle cabin to provide a more adaptable and comfortable ride. And this requires lots of materials in there, and lightweighting is very critical to that. But again, what I wanted to mention, we have to create the materials that are fully recyclable, because the goal is to go to a cleaner environment. And to me, these are the long-term, short-term, and long-term challenges to the industry.
Look, if I could jump in, I agree, and those are some very good points. The interesting thing that I see looking at the industry over the longer term, as as the companies have been looking at mass reduction and taking out a kilogram here and kilogram there, adding aluminum and things of that sort, like you mentioned, all of a sudden now in this new dynamic, we're being challenged to put in huge batteries and, things that all of a sudden dramatically will increase mass, which goes the opposite way. The other aspect is over time with regulations and with that have been requiring new, the new crash standards and things of that sort, plus all the added content that vehicles have been getting. That has also been a counterbalance to mass reduction because you're putting more stuff into the car, more modules, more electronics. So it's a continual battle, continual challenge. Robert or Jose, do you guys have some comments on this?
No, you're exactly right, Jacob. With the increasing mass of the batteries and then the ever more stringent safety standards in relation to range or gas mileage, it's a constant balancing act with manufacturing, with safety, with range or MPG to meet that balance. And innovation is the key. There's always a different way to approach a problem. You've got the Gen 3 materials that are coming out that are lighter gauge, higher strength, more conducive to cold forming. Increased uses of PHS steel, that at thinner gauges it is an advantage as well. And even tailor welded blanks, that there's nothing that's off the table when it comes to solving these problems. Because the bottom line is, customer safety and then value for their investment, which equates to range and miles per gallon.
But I think also we should consider as well as technology drivers. We have the emissions now. We have the benefit of having the vehicle, the electric vehicle, allowing for that it will provide some help on the emission side that we are moving away from the ICE engine. The cost, I think, cost of the materials now is also, it should be in part of that equation, because we have seen that even if we try to implement, even for chassis structures, composites, is really not really good for cost related, because at the end, when you try to put those materials into high volume production environment, it really costly, cost wise is not yet there, and that is something that we should also consider, as well as the materials that you mentioned already. That will be probably one of the first things to also add to the discussion.
That's a great point. I mean, that's one of the barriers, right? Which is what we're supposed to be talking about. So you can have all kinds of exotic materials and all kinds of solutions, but the cost is the challenge. I agree. That is a very, very big one. Are there any other barriers that you guys see that any other barriers to actually doing some of this mass reduction?
Just one more comment, just to add on to what Jose said. It's like you do have to put a price on, safety and range. Where do you draw that line? Because as Jose said, a composite vehicle, it is definitely more expensive, but yet it's going to be lighter weight and safer. So where's the price point where that is an advantage? That's the constant challenge.
Yeah.
Go ahead.
And you mentioned batteries, right? And we've seen that over the years, the batteries have decreased in size. It's going to be like the first cell phone that came out. There was a big brick, and now they're smaller. They're not smaller because people want to see a screen and things like that, but they could be smaller. And so if you see the evolution of battery over the last, I would say, 5-10 years, you will see that it has gotten smaller. So yes, we're going to electrical vehicles. Yes, we need massive batteries, but as time progresses, the batteries are reducing in size, which is going to be a plus for lightweighting the vehicle. We got to meet that range. right? And mass is against that meeting that range.
So that's a nice segue to I guess another kind of topic or question. So as we look at where we have to go, does numerical simulation, what kind of a role does that play, and what kind of methods, do you guys see in terms of selecting materials and using different materials? I don't know, Mario, do you want to start this one?
So as I said, I come from Ford Motor Company, and what I see, this is again my perception here in terms of numerical simulation, it has made a significant stride in driving design optimization in terms of using tools that can optimize for shape and for size, and of course with that there's a cost value effect, right? And so tools have been used to do that, and it's been like a combination of fine element analysis with multidiscipline optimization, MDO, and now we're linking with machine learning. Machine learning based on data that we may have from testing, in combination with data that we may come from numerical solutions. So that is providing now a way to maximize the weight reduction while balancing the critical functions for durability and MVH. Now, additional analysis software such as Digimat, and there's others in the market, have been used in order to allow for microstructure optimization, and we use plastic reinforced fiber reinforced plastic, and we've been using that to kind of tune the MVH, because now you can formulate the material so you can determine the best fiberglass content, the best fiber length or the optimum fiber length, and the orientation that you need in order to manipulate the design based on the material to provide the right damping characteristics. You want to, as you see a peak in frequencies of resonances, you want to provide at that frequency the maximum damping value. And so you can, through these tools, you can drive the design of the material as well as the design of the shape of the components such that mitigates the MVH effect. And at the same time, you have to look at the durability. So tools like that have been really essential, and they will be becoming more essential as we're trying to maximize the weight reduction. However, I have to say that although we have all that in place, OEMs, I think they're still using physical testing to do the final validation. The goal is, how do we do it without spending the money in physical testing, right? And that is still a challenge.
Well, CAE has really come a long way since when I started in this field. So it definitely has come a long way. And yeah, you kind of touched on that. That's that is the question is do you still need the physical testing? How confident are you that the numerical analysis is enough? And that's kind of a interesting point.
My belief it's a cultural thing with automotive companies, because when you go to aerospace, or let's talk about Jet Propulsion Lab, the Mars landing unit, everything pretty much is done through simulation, because they can't test here on Earth. They can test some parts, but from a system level, it's done by simulation. It's a cultural change that needs to be overpassed, because within simulation, as we apply now machine learning, and you can apply design for Six Sigma as part of that, you can look at the whole spectrum of variation in the manufacturing, how the casting or how the material is coming into place and look at the variational effect, which is better than testing one part to two part and then calling it we're ready to go as part of the DV process. And then later on we find out some issues with that. I think that has to still be incorporated. And the system level effect is very critical in the analysis, that it still needs to be plugged in more efficiently.
All right, thank you. I think Jose wanted to jump in.
Just a couple comments on that, Mario. Is you brought up the variation, and it's how well we're able to input the variation into the simulation models in order to get the repeatable or reliable results. You've got thinning in the stamp panels. You have maybe 4 or 5 suspect welds in a pattern. You have adhesive that isn't fully wetted out, et cetera, et cetera. As we go forward with simulation, adding those variables in there may yield to more repeatable results. I think in aerospace industry, everything they do is very strictly controlled, and maybe not as much innovation as what we are doing in the automotive industry with the ever-changing landscape with range and lightweighting and safety. So I would challenge simulation to comprehend more of the variation to get away from the actual physical testing, because I know on programs passed for OEMs, the actual physical results are much, much different than what's yielded in simulation, and getting that feedback in there going forward, that's where we can get away from it.
That's a very interesting point, Robert. I mean, and the other aspect is the customer. You have different, in the automotive industry, you have different customers with different expectations. Some people are very picky about one thing, other people are very picky about something completely different. And, you're trying to build thousands of vehicles, maybe millions, and you're trying to, have a solution for all kinds of customers. Some are, some care about a product, A or B or C, more so than maybe someone else. So, good points.
Some of the barriers that we see on simulation versus physical testing, correlation, is on the material side. We have to evaluate fatigue, crash, and MBH, for example. Those are the 3 major sciences that we have to evaluate. The first thing that you find out is if you move to a new material, getting the properties, properties for the correct analysis is one of the first things that you will find a huge wall, because some of the materials are not easy to get the fatigue properties to do your durability analysis. The other one, there are some materials that for the strain rates or some of the properties that you need for your crash analysis may not be that very easy to get at the beginning. So it's a huge cost just to get all that group of information to put it into your program, if you have to do it very quickly, because we have learned from that in the past that when we want to put new materials into the programs, is a huge work that has to be done on the side just to get all the properties from your new materials, especially if you want to move to composite, getting the correct analysis, and if you don't have the correct tools, basically you have to develop all of that to get at least some answers from your simulation, and then trying to get the next step, which is correlation between the two sciences, the physical testing versus the CAE simulation. And that's why we still have to do some of the physical testing, because you have to basically prove that our CAE is still, that is providing the robust solution that we want.
I just wanted to, I think you know this very well. When Boeing was developing their 787, which is a fully composite vehicle, I visited them at the time twice there, and we had a technical exchange. This was a major undertaking by them and a major technology challenge to put that in place, because they had all sorts of limitations. What happens in the airport where someone hits a plane and punches a hole right away rather than a dent. So how do they solve those things? And then the pressure on air and things like that. And they were able to, and they used a lot of simulation. They showed me this. They were able to put that in production, and now Airbus is, I believe, doing the same thing, or they already done it. They're going composite on major airplanes, and they took a lot of weight out of their airplane by doing that. They used all sorts of simulations to be able to do that. It's not the only solution, but certainly it's a way to drive the design and test the design.
Just remember that they have to make probably one airplane every week, and we have to make 2,000 vehicles a day or something.
And also, Jose, to that point, what's the development time for a 787 as opposed to the development time for the new F-150? Ford has to do that in 4 years or less, and I think Boeing has maybe 10 years to do that, and nearly unlimited resources and CPU time to do that simulation. And so they can refine that model to exactly the mechanical properties that they have. The challenge for the automotive industry is to do that in half to 1/3 the time that the aerospace industry is able to.
Yeah.
Good discussion. I mean, for sure, the auto industry can learn from other industries.
Yes.
And the aircraft industry over the years, they have done a lot in optimizing weight and things of that sort. But Robert, I agree with you. It is different in the auto industry, and you can't just apply everything from directly into vehicles. And if you take your F-150 as an example, you have different versions of that. You have different powertrains. You have different.
Oh yes.
So so the complexity there, right? You have different suspensions, different cab sizes and bed sizes, and it's quite a bit different. And then of course you have to protect for every single use, right? Some people will take it on a farm, other people will take it off road, someone else will be driving it, on a freeway, and we'll be expecting very quiet, a great NVH, for example, right? A very quiet vehicle. So the expectations and the usage cases are quite a bit different than, your Boeing 747, for example, that, it lands, it takes off, there are different weather.
Are we all losing Jacob?
Yes.
And I guess the point, the lesson we can take from aerospace is, how are they able to make those predictive models accurate? What does it take? And how do we apply that to our predictive models so that we can move away from physical testing?
Exactly.
So I think that technology exchange that you had with Boeing was excellent. Was Ford able to apply lessons learned for that?
Yes, definitely. And they learned from the automotive industry as well at the same time. It was, I think, a very even exchange of technical information.
And I think right now the auto industry can also learn. I mean, I'm sure other industries are also looking at the auto industry, but the auto industry can also learn things from the telephone industry, from electronics, from software. So this is not just the two industry game here, right? As things develop. So, okay, so I guess the next and this is kind of a nice evolving topic. So the next one is, Jose brought up the cost issue before, and we've talked about some of these different things here. How does an automaker, if we get back to, the auto industry, how does an automaker or a supplier, balance the cost, the performance, the aesthetics, as we try to drive, minimize mass, lower mass as much as possible, knowing some of the other trends that are going on, right? We talked about electrification or emissions or whatever. How can that be done? How do you balance this? Any thoughts? Comments?
So as Rob mentioned, that you have to make the balance, now that what the customer will pay, because sometimes, as we see from higher end vehicles, they go all in with the super advanced material, because they know that the customer will pay for that type of vehicle. But when you are specialized in the high volume, there is a limit, obviously, how much we could put on the material side, advanced materials, and then you also have to consider that you need to keep, you need to be competitive against the other OEMs or other your competition, basically, because the others will be putting very nice interior, very nice materials that they use. And I think at the end, the customer is the one that will suffer paying, the extra amount of money, but because the customer wants that particular material or that particular interior, or even if it is, like 10,000 vehicles for one particular configuration, the customer pays for that, even if you add, like carbon fiber body or something like that. The customer at the end, I think, is the one that decides, and your sales will tell this is basically what the customer wants. They will be paying for this, and that will allow us to implement more complex, more expensive materials. But in reality, the vehicles are mostly steel aluminum. This is our two materials that, at least in the automotive industry, is the two materials that we follow more closely.
In helping to balance that cost, thanks for the segue, Jose. But you're going to have the lightweighted materials, as Jose said, primarily aluminum. And if you're able to, commonize your grades, commonize your thicknesses, you're going to realize an economy of scale when you're purchasing that, and then you leverage your suppliers of that material, so that their production costs are less. Therefore, your cost per pound or hundredweight can be less as well. And from an aesthetic standpoint, you save on the weight of your closures, but maybe you're using a little more luxurious materials on your interior, which is where the customer is sitting, touching, and seeing, and so you're able to balance the aesthetics in that manner. And from performance, the same way. You're lightweighting in very specific areas, and you're making sure in performance, aka the battery, you're able to leverage that, for greater range. And from aesthetics, always bearing in mind the substrate that you are, designing, whether it be steel, aluminum, high strength steel, being very cognizant of the mechanical properties and how they react, in the forming or joining process. That'll help optimize your design as well as your performance, hand in hand with the weight.
Now, how would you guys see what's the importance of serviceability? When you choose certain materials and you optimize the gauges and the things, how important is serviceability down the road, replacing panels and things? To you guys, what are your thoughts on this?
I can discuss from the point of view of the frame, which is the lower portion of the truck. In this case, we have many components that are supposed to meet that part of the functional objective of the customer, that you have to replace those. So we have to be very careful with those, how we implement them for production, and then always considering the full life cycle, because there will be a point in time where where corrosion will be your worst enemy, especially for chassis components at the bottom of the vehicle. And I think this is one of our biggest concern always. And also for battery electric vehicles will be a same type of concern, because environment, once you put your structure outside, whatever material you decided to use, aluminum thankfully is more friendly to the corrosion environment, but it still suffers some of it, especially if you are mixing materials that we want to do that to get the correct low mass, and we can get into the issues of galvanic corrosion and some other problems that potentially could be there. And that it's also where serviceability is very important, because after 10 years you have to, components that have to be removed and then put back into the system. So that is extremely important in the design.
Yeah, I would agree. I mean, especially I think it's challenging when you mix materials.
Yes.
So the corrosion of single material is one thing, your typical rust or whatever, but and the aluminum may have not the worries of rust, but it has the corrosion, the galvanic corrosion issue. But once you start mixing materials, joining, fasteners, that's when things get also interesting in terms of corrosion. And I guess, which kind of leads to almost the next kind of question is, is there simulation out there that would help to pinpoint any areas or potential areas of corrosion or whatnot if you're designing materials?
Softwares that I'm aware of from different institutions, companies, that they try to simulate the corrosion of your part, but it's at the beginning of of the research. This is still on the research.
Yeah. I've seen some papers on that. By the way, that's a very interesting point that you're making.
Yes.
I've seen, and that's a challenge, I think, for simulation. I've seen some papers around that published, but I haven't seen applicability, at least my experience. And I go to a lot of conferences. I haven't seen anyone presented an application where they use that technology to predict corrosion under different types of environment, and so it's a very good point, and I think maybe it's a challenge to the software suppliers to work on that. That's a very good point. Yeah,
and especially with the lower thicknesses that we want to achieve, for the lower mass that we're trying to get, the smaller thicknesses take you to a further risk on the corrosion side, because you will be basically removing material from your thickness.
Yeah, and if there was a tool available, you would have to do that, post E-coat simulation where they do the fluid dynamics and the fill, in a road dip or something of that nature for coverage. Yeah. You'd have to take the result of that simulation and then move it into the corrosion sim to get an accurate result, if it existed.
Mm-hmm.
Mm-hmm. Or that's a challenge that somebody could take on one day.
Yep.
Yeah.
Right? Yeah. Right now we don't have that. It sounds like.
Yeah. So
good point. Anyone else have any comments on what we've covered here? Now I'll look at what. I guess another topic area we could talk about. We've kind of touched on some of these already. On some of the optimization strategies, I know some of that has been already brought up a little bit. Optimization strategies, both on the engineering or on the manufacturing side. Is there anything to add? Either of you have anything to add on that point?
Well, go ahead.
Go ahead.
So I mentioned that there's a lot of technology there for MDO on different types of either metals or now composites or plastics, and in combination with design from Six Sigma methods, where you look at the effect of the variation in manufacturing, allows us to do a better prediction. Again, driving the minimum weight for the target or the objective stiffness requirements and stress requirements, right? So that is being applied today. There's a lot of, I think all the OEMs use that quite effectively. Yeah. And there's a lot of softwares that can do that kind of work in terms of optimization software and, of course, multiple FEA methods and things like that. Mm-hmm. So
that's probably a good starting point. And then depending on what the individual designer or engineer is doing, probably would need to adjust that for their specific target, right?
Yeah.
Mm-hmm. I mean, it depends what segment you're going into or what the usage is. Unless I haven't seen the software, unless the software is complicated enough where you could put all those variables in.
No, it's basically your different sciences. You put it in one software. So one software is doing several iterations and calling your crash, your fatigue analysis, your MVH, and all at the same time, and doing the optimization for your component.
So you define the design space that you need, right? Mm-hmm. And based on that, the software will automatically tell you, based on your design objective, will tell you what the shape will be and all of that. The thing is, the challenge is sometimes it comes up with a shape that you cannot manufacture. So you need to involve the manufacturing phase of it as well to make sure you come up with something that is practical and cost-effective, not only in the cost of the part, but cost-effective in the manufacturing portion of it. Mm-hmm. It's not something that you push a button. It requires several experts in different areas to work together and bring this about.
Yeah. As we touched on this one also, as the industry is adding electrification into their portfolio, okay, whether it's adding, you're adding batteries for sure, some kind of electric motors, some other kind of switching devices and things, whether you're adding that to a existing engine, so hybrid, plug-in hybrid, it adds mass, right? Or if you're doing an EV, so you don't have to worry. You take the engine out, take the transmission, the fuel tank out. You put in all those electrification components, which requires a bigger battery, still probably a bigger motor and stuff like that. What are your guys' thoughts, as we tinker and taking out, a couple kilograms here and a couple kilograms there and changing the gauge, and what do you guys see, as far as when all of a sudden we're adding in all this mass into some of the applications? What do you guys see as kind of, how is this impacting the industry, and how do you optimize that? Because invariably, at least with today's technologies, it does add mass. Would you guys agree with that? And what, you have any thoughts on that?
I do, and it does add mass, but the innovation lies where if you take those, the battery structure, the structure of the vehicle, and if you integrate them and have them work together and achieve your safety requirements, basically they're not separate systems. They have to be viewed as one cohesive system of performance where, like you were talking about before, Mario, the NVH, the durability, the crash, that all has to be optimized, because if you are duplicating structures, you're adding unnecessary mass. You have to have all those areas of the vehicle of design working hand in hand and make sure that you don't have redundant areas in your critical, safety path, and then where your powertrain is being held, per se. That's where, it does add mass, but working together, for the final result, which is basically a lightweight, high-performance, long-range vehicle, it can and should be achieved. It's a different mindset.
Yeah, I see. I agree. I see what you're saying. So basically, if you're designing for it and optimizing it from the very beginning, you can gain a lot of efficiencies. As opposed to if you just drop the engine and the fuel tank and replace that with, fit into that same space, whatever it is that we're talking about. Yeah, I agree. Jose?
So going to the challenge, I worked in the powertrain side at Ford, and the challenge of going to the fully electric motor was the motor whine, and the gear whine from the connecting gearboxes there, and normally the NVH engineer wants to put all that structure there and all of that to attenuate that, but then that goes against the weight and the range of the vehicle. So a lot of analysis and iterations were done to minimize, to come up with the thinnest, with the proper ribs in the right places in order to mitigate that the gear whine noise, both on the motor side from a motor whine and the gearbox that connects to it as well. And how do you do that as a system? And then you have to drop it in that cradle, right? Then what is the material of that cradle? Can we make that cradle not non-metal? Will that survive and things like that? So that is still a challenge there to ensure that you deliver the mass requirements or objectives of the vehicle, and still be able to deliver the functions and attributes required. The NVH, the durability, and of course the range, which is critical.
Mario, you bring up a good point. So when we have an internal combustion engine and a nice exhaust note that everyone likes, it kind of hides a lot of the...
It does, masking, yeah. It's a masking effect,
yeah. Take that away, and if you want an EV, all of a sudden you hear these noises you never heard of before, and now they bother you, right?
Yeah. Well, we had them in the internal combustion engine, those whines, but they were all masked away by other noises.
Exactly.
So you hear that profound, powerful noise, but they had a lot of hidden, unwanted noise in there. Now with the motor, right, it's clean, and you hear that motor whine, and you hear that gear whine in the box.
Tires,
it's all exposed, right?
So that acoustic dampening adds mass, right?
Yes.
Yeah.
Another problem, right?
Yeah.
So you need lightweight acoustic dampening, and the question is, do you need more of it for an EV than you did for an internal combustion engine?
Yep.
What's the question? I mean, what's the answer? Do you need more of it, or you just need it in different places? I don't know. It's an interesting topic. It does bring.
Yeah. So what a lot of companies, your companies, do as well. You put acoustic covers around it in some areas. You put acoustic covers that will dampen that, but what happens to the cost? Cost goes up, and you got to balance that as well.
Cost and mass.
You got to balance that. Can you afford it to do that? So there are solutions, right? So how do you come up with the most cost-effective solution?
Right, exactly. I'm just looking at the time here, and I'm looking at what else we could still talk about. We've talked a little bit about materials, and maybe I'll just touch on the materials and joining technologies or techniques. Can you gentlemen talk about some of the thoughts around the joining and material techniques that maybe you're seeing as having potential?
So in general, as we mentioned in early, that steel has come up with probably the last 3 years with very good advancements. Now we are seeing very good steel grades that are very competitive. And we know, as mentioned, steel and aluminum, those are the two materials that they are mostly the most important for the structural components that we build for design. And what I see is on steel, thanks to these new developments that they are doing with the materials, obviously now it comes the problem of joining them together. If you are planning to have components like suspension or trailers attached to aluminum, for example, attached to your steel components, the easiest and more simpler way of joining is fastening. Any type of fastener that will be the first type of joining.
Like rivets and things like that.
Yeah, for
mechanical joining.
Mechanical joining, yeah, because for example,
mass.
Yes, it's mass, yes. And there are other structures where because of the high volume production, we have to consider. In the case of steel, with welding. Arc welding is your fastest way of producing many components during the day.
And no mass.
And no mass. Yes.
How about multi-material joining? Welding, adhesives, any thoughts on some of that stuff? That's where it gets interesting as far as I'm concerned.
Yeah.
In the multi-material joints, you have the adhesive mass, and then you do have mechanical fastening, which is additional mass. So in many cases, it can offset your mass, say, by using the less dense substrate. Now, so that has to be, and I hate to use this word, it has to be weighed against the other options. Your traditional, aluminum spot welding, resistance spot welding, laser welding in the correct application. I think they still have a place moving forward, even in a lightweight electrified vehicle.
Yeah.
And the adhesive and the self-piercing rivet. Yeah, there's a cost for each one of those rivets, and then you have the adhesive as well. Although there is a lot of adhesive throughout even a resistance spot welded body also.
Yeah.
What about the usage of magnesium? For example, at Ford, we had transfer cases and even some transmission cases that were magnesium from a light, but the cost increases though. So
but for
again, it has a cost effect, right?
It's not, the modulus is not that high. It's
yes. Yeah. I'm talking about in terms of castings, and of course you gotta have the right ribbon pattern to get that stiffness.
You have to
but that has been used, right, at a cost effect. It's got
good for mass, but it adds cost obviously, and it has.
And then manufacturing has manufacturing challenges as well.
But I think if you're joining that mechanically, it's less of an issue. So if it's a transmission casing, or if it's maybe less of an issue than if you tried to make magnesium cross members, for example.
Oh, yeah. Well, it will not have the stiffness.
Right.
But for a case or something like that, it will work. Again, you got to be very careful with what you're joining that to, right? Yeah. You got to keep that consistency and keep that stiffness joint the right in the right proportions.
In magnesium, it has been used on closures that are out of the crash critical path very successfully. Swing gates, lift gates, etc. And that basically it's a component unto itself, hemmed to likely an aluminum outer, and mechanically fastened via bolts to the hinges and then to the body. That's where magnesium definitely has a place.
And you could isolate it pretty well too if you're worried about any corrosion to anything. So
Yep.
Does additive or 3D manufacturing, does that somehow interact with lightweighting efforts?
I was thinking about that, and there will be advantages with 3D printing, additive manufacturing, as the cycle times decrease. What we were talking about earlier with the the non-manufacturable type shapes and structures, you can create many of those by the layering of additive manufacturing. However, the cycle times right now prevent it from being viable for high volume or even medium volume manufacturing, other than basically just serial 3D printers all the way across. But as that industry progresses and they're able to lay down material faster and faster, it will become prominent in not just automotive manufacturing, but all phases of manufacturing. It's going to go more towards a very much a raw material is shipped into the plant, and then 3D printers pretty much spit out everything. I don't know if it'll be my lifetime, but I certainly hope it will, and that's what we can look forward to in the years to come.
Yeah, I 1,000% agree with you there, Robert. As I mentioned to Jacob, I have mixed feeling. It's a great technology. You can really reduce the weight. It will give you the skeleton and everything. But then, how do you manufacture that for 1 million vehicles?
Slowly.
The technology. I mean, if you have 1,000, maybe we do it for prototype parts and things like that, where you have just a small sample. Just to build a prototype, it's good, but to take it into production on 1 million vehicle plus, the technology is still not there to do that printing fast enough.
We look at the predictive simulation software. 20, 30 years ago, it was rudimentary, and people said it would never work. And look at it now. They're going directly to production in the aerospace industry just from predictive analysis. Semiconductors and chips, what is it? It doubles, how many months? I don't know what it is, but additive manufacturing is going to make the same type of exponential progression as time passes.
Yeah, the thing I can think in addition to what you both said is, prototyping for sure. 1 million pieces or millions of volumes, no. But when you have all of these low volume versions of things, there could be some potentials to use it for some specialty low volume sale to customers of some parts and components, and the tooling might be overall for low volume, it might be cost might be quite reasonable depending on the usage. So there's that variance. We don't have to talk about millions necessarily for the low volume. I guess that would be my thought.
Jacob, process check. I thought that in 40 minutes we were going to have a Q&A session. I think we passed the 40 minutes mark. Do you want to, I'm not sure, do we want to ask for questions from the audience?
Well, I'm watching the,
the Q&A.
So we have 60 minutes for this. We have, looks like we have another 6 minutes left. Over 1 hour. Oh, there's Mark, right on cue. So I'm watching the Q&A, and I didn't see any. So we must be doing such a great job that we're just answering everyone's questions. Questions welcome. So if anybody has any questions, please let us know now, I guess. Mark, I haven't seen any. Have you? Do you have some other ones?
I think you've hit the nail on the head, Jacob. I think you've done such a fine job of asking questions and keeping the conversation going that there doesn't seem to be any questions coming through. We do have another 5 minutes, so I would encourage the audience for the last 5 minutes, if you've got any questions, please pose them. There's a Q&A functionality on the right-hand side. Just tap your questions in there, we can pick them up.
Or any interesting comments, I would say, from the audience.
Yeah, but in all seriousness, I mean, this has been a really interesting discussion, by everybody. And okay, looks like we've got some question here. So, Mark.
So, yeah, we have a question about material selection. So couldn't tools like Granta or Material Center be of help for this? Cost, manufacturability, and many other criteria could be used to select materials.
Anybody want to take this on? I'm not familiar with...
I'm not familiar with Granta or Material Center.
I'm not either. Perhaps the person that is asking the question can address it.
It looks like there's someone in the audience that can.
Yeah. Sylvain Kalmos?
Ahmed. Maybe it's Granicoat, but I'm not sure.
Yeah.
We do have another question. Do we want to move on from the first question?
Yeah, thank you for the invitation at first and for the discussion. It's very, very interesting. Yeah, I come back about my question is about one remark from Jose about the difficulty to do the material selection because you expect from one material to have certain strain rate dependency, for example, or certain capability in terms of strength, and it's difficult to do this choice prior to any CAE operation. And also, at first, I have to say I'm not a provider of any software of any kind, but I had a presentation about one of them. In this case, it was Granta, and I didn't know this kind of tool, but I've been very amazed. But by all the kind of criteria that we can use in this kind of tool to select a material. As I said, you can select the cost, the manufacturability, the type of application that you want to use for which you want to use this material. So I see that as something quite powerful, very in early stage of design, very early, where you can do a first selection and help the CAE teams in going into, let's say, the first good directions and avoiding some mistakes.
Okay.
Thank you, Sylvain. Very good information.
Thank you.
It looks like there's two more questions there. I can take the last one from Arn. The challenges of the joints, for screws in lightweighting solutions. Number one, it's accessibility. Number two, it's durability over time. And then it is the weight and the cost. So basically, it's all the above for what you're asking there, Arn. However, in some areas, it is the only solution. So it is an option in cases of that nature.
Yeah, I think I agree. It depends on the application, depends on the usage, the joint. It's hard.
And they need to be minimized, for just because of everything that was listed there.
Yeah, I agree. Both. So the answer would be yes. Yes and yes.
Yes. Yes.
There is another question here asking about battery resizing. Have you seen fewer barriers to lightweighting on BEV vehicles is kind of the question. I can start. Batteries have come a long way over time, right? I laugh when people say, we've got this new technology called electrification. Batteries have come a long way. So certainly in many ways, you can put a better battery with more power per weight on board. Are they there where they need to be? No, I don't believe so. And there's still ways to go. Robert or Mario, Jose, any comments?
So my take on this, yes, battery is getting smaller, resizing, but I come from the powertrain side. We had the challenge to deliver these motors with very stringent target objective for mass, and we had to do a lot of optimization to deliver that weight independent of the battery. But then the thing is, the range is still the challenge, right? As you go from, we used to be at 100, at 200, 300 miles, they want to go to 500 and even more. So yes, we still have a major challenge for lightweighting. We got to maximize that range, that driving range for the vehicle owners.
Yeah.
But also that if you consider that some of those batteries are in the range of 700 kilograms, 800 kilograms, it's almost a payload in your vehicle now. So that makes it a little bit more complex to design, if you want to do lightweighting, because now we have to actually increase thickness for that new mass. We hope that the battery systems will start getting lightweight as well, with their materials, less copper, or the way you utilize the copper, the sizes of your thicknesses there, allow us to get the weight as well there, because right now it's a little bit complex.
Yeah, I agree. Mark, time check. I know we've got Ahmed that just joined. Are we still good on time?
Yeah, I think so. The next session starts in 3 minutes, so I think if we hand over to Ahmed, and then we can close it off from there.
Perfect.
Okay, very good. Thank you.
You're on mute, Ahmed.
No.
Oh.
You should be able to talk now, Ahmed.
It's not working.
We can see you.
Keep talking, we'll read your lips.
How about now?
Now.
Yeah,
Okay.
now.
Okay, good. So I'm going to make it really quick to answer that question that was mentioned above. Both of those tools are meant to be used for something like this. It is a life cycle management platform, whether it's Grant or Material Center, where you can store data, you can store any data from the raw materials test data all the way down to the product levels. You can also integrate with any tools, check for compliance, substance level controls, and store all type of data that when it's very customizable. You can include costing and manufacturability as well. So with a couple of few clicks, you can substitute materials with any of your FEE models and take into account any changes and effects it will have on the final product. Both of tools are very good. Obviously, I'm Team Material Center because I'm MSC Software, but Grant is a very good tool as well, and they can do the same thing.
Very good. Thank you.
Thank you.
Yeah.
Thank you.
Pleasure to be here.
Well, with that, any final words there, Mark?
No, I think that concludes the session. So the only thing I'd like to say is thank you very much to all of the panelists. I think it's been a really good session. Nice to see the audience asking questions towards the end as well. But I think you did a great job of steering the conversation, Jacob, and certainly there's a hell of a lot of experience in the room. You can certainly tell.
Oh, yeah.
So thank you very much. Are you all sticking around on the platform for a short while?
Yes.
Yeah.
Yeah.
Thanks,
So,
everyone.
Thank you very much. It was a pleasure. It was very, very good talking to all of you. Thank you.
Thank you. Pleasure. Likewise. Yeah.
Take care, everybody. Thank you very much.